Problem in ordinary differential equations describes how the amount or concentration of a substance in a container changes over time when fluids with different concentrations flow into and out of the container. The fundamental principle applied is that the rate of change is equal to the rate in minus the rate out. This process is modeled using a first-order linear differential equations, which is typically solved using the method of separation of variables to determine the amount of substance at any given time. A logistics company managed a fuel storage tank used for delivery trucks. The tank initially contains 500 liters of fuel with 20% biodiesel. A new fuel mixture containing 30% biodiesel is pumped into the tank at a rate of 10 liters per minute, while the mixed fuel is drained from the tank at the same rate to supply trucks. Let YT be the amount of biodiesel in liters in the tank at time t minutes. Number 1. Determine the initial condition and formulate the differential equation that models the situations. Number 2. Find the amount of biodiesel in the tank after 30 minutes and state the long-term amount of biodiesel in the tanks as t approach to infinity.
For this study, we have two main objectives. First, we want to provide an in-depth understanding of mixture problems, especially those that involve differential equations. Second, we aim to develop a systematic and organized method to solve mixture problems even when they involve higher-order differential equations.
Let YT represent the amount of biodiesel in liters in the tank at time t. At time 0, the amount of biodiesel in the tank is Y0. Biodiesel flows into the tank and out of the tank over time. The rate at which biodiesel enters the tank is called Rin, and the rate at which it leaves the tank is called Rout. The rate of solution entering the tank is given by dL over dt, and the concentration of biodiesel in the inflow is dy over dL. The change in the amount of biodiesel over time is described by the differential equation, which is dy over dt equal to Rin minus Rout. This equation tells us that the rate of change of biodiesel in the tank is equal to the rate entering the tank minus the rate leaving the tank.
Next, I will continue explaining about the method of solution for the first problem statement. The first problem statement requires us to find the initial amount of biodiesel. Based on the given information, there is 500 liters of fuel containing 20% of biodiesel, which can be calculated as 20 over 100 times 500 equal to 100 liters. Now, I will proceed with the steps to find the first linear differential equation. In order to do that, we need to gather out all the information given. For the inflow process, the rate of solution entering the tank in a minute is 10 liters, with the biodiesel's concentration of 0.3. On the other hand, the rate of solution for the outflow process is 10 liters. From the question, the concentration is not given for the outflow process, so in order to complete the linear differential equation, we need to form an equation of y over 500. Then, multiply both of the rate of solution and its concentration for both inflow and outflow to get 3 and y over 50 liters per minute respectively. Finally, to achieve our first objective of getting a linear differential equation, we need to subtract the product of the rate of solution and its concentration for the outflow from the inflow process. Then, we will get a linear differential equation of 3 minus 1 over 50y. From the differential equation, we can find out that P is equal 1 over 50 and Q equal to 3. In order to find the integrating factor, we just need to follow the formula of exponent power of integration of P dt, and after substituting the value of P with 1 over 50, we will get a solution of exponent power T over 50. The third step is to equalize the differential of y with q value before multiply both sides with the integrating factor value that we have got earlier to get the value as follows. Then we need to integrate both sides. On the left hand side, integrating differential of y times exponent power t over 50 will resulting in y times exponent t over 50. While on the right hand side, integrating 3 exponent power 1 over 50 will resulting in 3 exponent power t over 50 over 1 over 50. Next, in order to find the equation for the amount of biodiesel in a certain time, we need to divide the right hand side with exponent power t over 50, which then will be equal to 150 plus t over exponent power t over 50. At this point, we cannot leave the calculation until there only because we need to find the value of C to completely obtain the equation. So, we need to substitute the y value with 100 with the initial condition of t equal to 0. After we have done the calculation, we will finally get the C value equal to negative 50. Therefore, the final equation to find the amount of biodiesel at certain times is equal to 150 minus 50 over exponent t over 50. Now, I will proceed with the second problem statement where we need to find the amount of biodiesel in the tank when t is equal to 30. All we need to do is just simply substitute the value of t with 30 in the previous equation. After substituting it, we will get y equal to 150 minus 50 over 1.8221 equal to 122.56 liters. Moving forward to the last problem statement, when the question requires us to find the long-term substance, we just need to substitute t with infinity, resulting in y equal to 150 minus 50 over exponent infinity over infinity. Since any number divides with infinity will become 0, we will get an equation of y equal to 150 liters.
Basically, this is the overall discussion for question 1. In conclusion, the mixture problem was successfully represented using a first-order linear differential equation. The formulation of the model allowed us to describe the change in the amount of biodiesel in the tank over time. By obtaining the solution y at t, we were able to express the quantity of biodiesel as a function of time, which confirms that the mathematical model accurately reflects the physical situation of inflow and outflow. This result demonstrates that differential equations are effective tools for analyzing mixture system involving continuous flow. Next, this is the overall discussion for question 2. To conclude, the solution y at t was further used to evaluate both the short-term and long-term behavior of the system. By substitute t equal 30, the amount of biodiesel in the tank after 30 minutes was determined, providing insight into the system at a specific time. Furthermore, by considering the behavior as time approaches infinity, it was observed that the system reaches a steady state condition. The steady state value indicates that the amount of biodiesel in the tank will stabilize over time regardless of the initial amount. Overall, the discussion highlights how mixture problems can be systematically analyzed using differential equations. The result obtained not only provide numerical answer, but also help in understanding the behavior of the system over time. This study reinforced the importance of mathematical modeling in real-life applications, particularly in predicting equilibrium conditions in mixture processes.